So, teams use Redis for caching, for sessions, for rate limiting, leaderboards, queues, PubSub, and distributed logs. And that is a strange list, right? Because those jobs do not need the same thing at all. A cache can lose data and build it. A payment system cannot. A live dashboard can miss one update and recover on the next one. A job queue may not be allowed to lose anything. And yet, we keep reaching for the same tool for all of them. So the useful question is not what Redis can do. Redis can do a lot. The useful question is what kind of problem is Redis designed to make easy and what are we quietly giving up when we choose it. And that is the video, not Redis internals, not the source code, not a benchmark on how many commands it can run. Just 8 trade-offs that helps us decide where Redis fits in the system and where it does not. Most of us first meet Redis as a cache. You put a value behind a key, read it quickly, give it a time to live, and stop hitting the main database every time. And that is useful. But I think it misses the more interesting part. Because Redis does not only store values, it understands useful shapes, counters, sets, lists, hashes, sorted sets, and it gives you operations on those shapes. So, let us say we are building a leaderboard. One option is to store it as a blob. When a player scores, our application reads the blob, changes the score, sorts it again, and writes it back. And that already sounds awkward, right? But the real problem is what happens with two app servers. They both read the old value, they both make their own change, and the last write erases the other one. With Redis, we do not move the whole leaderboard into our application. We tell Redis, increase this player's score, and Redis performs that change where the shared data already lives. And the same idea shows up in rate limiting as well. Instead of every app server keeping its own counter, all of them update one shared counter. So the limit applies across the whole fleet and not separately on each machine. So the first design lesson from Redis is this. When several servers need to change shared state, do not always move the state to the code. Sometimes move the operation to the state. And that saves you round trips. But more importantly, it removes an entire class of race condition. And the cost is that Redis is not a general query engine for your data. It is excellent when you already know the shape of the question. Increase this counter, add this member to a set, give me top 10 scores, tell me whether this key exists. If the product team asks a new question next month, show every customer in Bengaluru who bought 3 products in the last 90 days. That is a database problem, not a Redis problem. So use Redis when the access pattern is known and narrow. Do not use it because you are hoping it becomes a flexible database later. Now, there is an obvious question hiding inside what we just said. If two servers send increase this counter at exactly the same moment, why does that actually work? Why do they not collide? And the answer is the second trade off. Redis runs your commands on a single thread. One command finishes completely before the next one starts. So there is nothing for you to lock because there is nothing to race against. And that is where all of those atomic operations come from. And before somebody says it's in the comments, yes, newer versions do use extra threads to read and write the network sockets. But the part that touches your data, actually running the command, is still one at a time. That has not changed, and it is not an accident. And the cost of that is the thing that you feel in production. If there is one thread, then a slow command does not slow down itself, it stops everybody. And the classic example is the keys command. Keys star works every single key in the database, and on a small database, it feels instant. So it quietly gets into somebody's debugging habit. Then the data grows past 5 million keys, and the same command is now taking hundreds of milliseconds. And for that whole time, every other client is not slower, it is waiting. And think about that at a scale properly. If you are serving 1 lakh operations a second, 400 milliseconds of blocking is around 40,000 requests that all just got 400 milliseconds slower. Your dashboard lights up across the whole application and nothing in your application changed. So the practical rule, never run keys in production. Use scan instead. And the difference is not that scan is faster, it is that scan hands you back a few keys at a time and lets you come back for more. So the work gets broken into small pieces and everybody else gets served in between. And the same idea applies elsewhere as well. Deleting a huge set or list blocks the server as long as it takes. So there is a version of delete that hands the work to the background instead. And any script you run holds the server for its whole runtime. So on Redis, slow and blocking mean the same thing. The third trade-off is simple. Redis is built for data that your application needs quickly and repeatedly. And the common property of a good Redis use case is not that the data is small. It is that the data is hot and that losing it or rebuilding it is survivable. So that gives us much better way to decide whether something belongs in Redis at all. Ask two questions. How often is this data used? And what happens if it disappears? And the answers separate things quite cleanly. Keeping a user session in Redis is reasonable. If it is lost, they sign in again. That is annoying. But the business is still correct. Keeping the only copy of an order payment in Redis is completely different thing. If that disappears, we do not have a cache miss. We have lost business truth. So the third lesson is separate the system of record from the fast working state around it. Your durable database owns the order and Redis can own the checkout session, the rate limit, the cache product details and the idempotency marker around that order. Redis gets much easier to use the moment it is not carrying something the business depends on recovering perfectly. And there is a cost to keeping things in memory that people find out late. You are not only paying for your data, every key carries bookkeeping along with it. And you do not have to take my word for that. Set a key with a 3 byte value and run memory usage on it. You will get back something in the region of 50 to 60 bytes for 3 bytes of data. That is the tax. And you can measure it on your own box in about 10 seconds. And if that matters at your scale, the fix the docs recommend is to group your objects into hashes instead of giving everyone its own top level key. So you stop paying that per key tax 1 lakh separate times. One caveat though, keep those hashes reasonably small, say 200 or 300 fields, not 1 lakh. And the last part of this one, I would genuinely go and check on your own setup today because out of the box, Redis has no memory limit at all. It keeps allocating until the operating system kills the process. And if you do set a limit, the default behavior is to start refusing writes while still serving reads. So your cache fills up and then stops accepting new entries, which is exactly the moment a cache is least useful to you. Redis gives you atomic operations. An increment happens as one operation. Setting a value only if the key does not already exist happens as one operation. Adding a member to a set happens as one operation. And that is a big part of why Redis feels so convenient for coordination. But there is a line here that is very easy to cross. An atomic Redis command does not make your whole business workflow atomic. So imagine we are processing an order. We take a lock in Redis. We charge the customer. We update inventory. We mark the order complete. And that is four different systems and several network calls. Now, Redis can stop two workers from starting the same work at the same time, but it cannot turn that whole workflow into one indivisible action. A worker can still crash after charging the customer, but before updating the order. A lock can expire while the work is still running, and a failover can create a window where another worker also believes it can go ahead. And this is also why Redis transactions surprise people, I think. Multi and exec do not roll back. If one command in the middle fails, the rest still run. What you actually get is isolation, meaning nothing else interleaves with your batch. Not atomicity in the database sense, so hold it as these run together uninterrupted, and not these all succeed or none do. So, a Redis log should reduce duplicate work. It should not be the only thing protecting correctness. The thing being protected still needs its own defense. Payments should use idempotency keys. Inventory should reject an invalid second update. The database can use a unique constraint or a version number, and a worker should always be safe to retry. And this is a much bigger distributed system lesson than Redis itself. Coordination lowers the chance of a conflict. Idempotency and constraints decide what happens when the conflict occurs anyway. So use Redis to coordinate. Do not use it as a proof that a complex workflow can only ever happen once. One of the nicest things about Redis is that a key can expire on its own. A session can live for 30 minutes, a verification code for 5 minutes, a cached response for 1 hour, so it is natural fit for temporary state. But there are two different ideas hiding inside that. The first one is after this time, the value should no longer be returned. And the second one is at this exact moment, some business action must happen. And Redis expiry is good for the first one. It should not be your only mechanism for the second. So let us say a reservation expires at 4 p.m. It is fine for the cached entry to stop being usable around then. But if the business needs to send a refund, release the inventory, notify another service, and write an audit record at 4 p.m., a disappearing key is not a workflow engine. Nothing runs when a key expires. It just stops being there. So use a scheduler or a durable queue for the business event and use the time to live for the temporary state. And honestly, keeping those two separate in your head will save you a whole class of bug. And there is another practical thing here as well. Do not give a huge number of popular cache entries the exact same expiry because when they all expire together, every request misses together and all of those requests fall through to your database together. The cache was supposed to protect the database and now it has created the spike itself. So add a bit of randomness to your expiry times. Do not set them all to exactly 3600 and make sure your application can rebuild a missing value safely because at some point it is going to have to. So the fifth lesson, a time to live tells Redis how long some state may remain useful. It does not replace scheduling or durable delivery, or having a plan for a cache miss. Redis can persist data and it can replicate data to other machines, but those two words can make us assume a much stronger guarantee than we actually choose. Persistence means Redis has ways to recover data after a restart or a failure. Replication means another machine receives copies of your writes and you can take over when the primary dies. And both of those are genuinely valuable, but neither of them answers the question that actually matters. And the question is this: did the system wait long enough to know this write was safely somewhere else before it told your application that it succeeded? Because with asynchronous replication, there is a gap. The primary accepts the write, your application receives success, and then the primary forwards it to the replica. So if the primary dies in between, the replica gets promoted without that write, and your application was already told it worked. And that does not make Redis broken. It means Redis chose lower latency over waiting for another machine on every single write. And their own documentation says this plainly, by the way, that it is possible to lose writes which were already acknowledged. It is written down. Most people just have not read it. And for a cache or a session or a rate limiter, that is exactly the right choice. For money, for inventory, or for final state of an order, it is usually the wrong place to make the trade. So the sixth lesson, do not ask only whether Redis has persistence or replicas. Ask what loss window your application can actually survive. And if the honest answer is none, then the source of the truth should live in something designed around that requirement. Redis can still sit right next to it and make the whole thing fast. It just should not be the only place the truth exists. Redis gives us a few different ways to move messages around, and they are not interchangeable at all. PubSub is the simplest one. A publisher sends a message to whoever is listening right now, and that's a good fit for live signals. Reload this configuration, invalidate the cache entry, update this dashboard, show the user is online. In those cases, losing one message is acceptable because the next update repairs it, or the receiver can just fetch the current state again. And there is a detail here that catches people, which is not the obvious one. It is not only about a subscriber being disconnected. A subscriber that is merely slow gets disconnected. If it cannot keep up, Redis lets its backlog grow to a limit and then closes the connection on it. So now imagine using the same model for a payment job. The worker disconnects for a moment, the message goes out while nobody is listening, and the payment job is simply gone. That is not performance problem, that is wrong delivery model. So, when a message has to survive a worker restart, you need stored messages, acknowledgements, retries, and a way to recover unfinished work. And Redis streams give you a real amount of that. The message stays in pending list after delivery until the worker says it is done. So, if that worker dies, somebody else can pick it up back. And when messaging becomes a serious system of its own, delayed jobs, several consumer groups, long retention, large backlogs, replay, proper operational tooling, a dedicated broker is the clearer choice. A stream is one key, and one key lives on one node. So, a Redis stream does not spread itself across machines the way a Kafka topic does. So, the rule I would use is this: if the next message can repair the loss of this message, PubSub may be enough. If losing the message would create missing work, use a durable stream or a proper broker. Choose your messaging from the failure behavior and not from how easy the first demo looks. The last trade off shows up when Redis grows past one mission. Clustering spreads different keys across different nodes, and that genuinely helps when your work is spread across many independent keys. But it does not make every workload scale automatically, and I think that is where people get caught. Because one extremely popular key is still one extremely popular key. A single key lives on single node. So, if all your traffic goes through one counter or through one very large customer's data, adding machines does not help at all. The problem is not capacity. Everything is landing in the same place. And there is a second thing clustering takes away, which is more concrete. A command that touches several keys only works if all of those keys landed in the same slot. And if they did not, Redis simply refuses to run it. There is an error for exactly this, called cross slot. Now, you can force related keys together by fixing them a shared tag in the key name. But notice what that means. You are now handwriting your own sharding scheme inside your key names, and whatever you group together can become your next hot node. So, before reaching for clustering, look at the key design instead. What is the natural unit of traffic? Can one tenant become much large than all others? Does a single request need one key or 20 related keys? And are we creating a global counter that every server has to update? Because adding machines helps when work can be divided. It does not help when the design forces all of the work through the same piece of state. And that lesson is much bigger than Redis, honestly. Sharding is not a substitute for choosing a partition key that matches your workload. So, when I am deciding whether Redis fits some part of the system, these are the questions I would actually ask. First, is this data hot enough to deserve a fast shared store? Second, can it be rebuilt, retried, or recovered if Redis loses it? Third, do we know the access pattern in advance, or are we going to need flexible queries later? Fourth, can the important change happen as one atomic operation, or are we pretending that a multi system workflow is atomic? Fifth, what actually happens if a write or a message disappears during a failure? And sixth, will this workload spread across many keys, or will one hotkey receive everything? And good Redis use cases usually have a clean answers to those. The data is hot, the operations are narrow, the state is temporary or derived, a small loss window is survivable, and the work can be divided. Bad Redis use cases almost always start from convenience. We already have Redis, the command is only one line. It was fast in the demo. And then much later, we find out that the application needed guarantees nobody ever asked Redis to provide. So that is the way I would hold Redis, not as a cache, not as magic fast database, not as something we would have to understand line by line before we are allowed to use it. At high level, it is a set of trade-offs. Shared operations instead of flexible queries, hot working state instead of permanent truth, coordination instead of complete workflow correctness, expiry instead of scheduling, low latency instead of strongest durability, and simple live messaging instead of guaranteed delivery. Once you know which side of each of those your system needs, choosing Redis gets much easier. And sometimes the right Redis design is not to use Redis at all.